I'll brighten it up. All right, guys. That's good. Lucas, thank you for reminding Willow to tell me to record. All right. So, these are terms. And I don't typically give terms, and I don't give definitions on a test, okay? What we are going to do, a lot of this is common sense stuff you know. What we are going to do is we're going to go through all this, and we're going to make comments about it and give examples. On your exam, how this will be tested will be things like, which of the following is an example of sublimation? And then give you choices. Or, when da-da-da-da-da happens, this is because of da-da-da-da condensation, or whatever the answer is, okay? So I will not give you just straight up definitions ever on a test. I will not put sublimation, give me the definition, never. What I will do is you have to understand it. This is like the lowest level. It's the lowest level of learning is like memorization, which is necessary on a lot of things. The next one is just being able to find an example of something. That's what this is. It's not like rocket science stuff here. But what I'm trying to get you to realize is you know a lot of this stuff. It's just like the gas laws. You knew the gas laws, what happens. You just didn't know they were gas laws. You didn't know how to put the numbers with them. And that's what this is. So our whole concept today, and for this section, which is your last section of material, the whole concept here is at the beginning, it's a lot of terminology, understanding the terms of solutions, and then we're going to get into the math. And so we've got like 2 pages, a page and a half of terminology, and then all the rest of this is math problems, and that's it. That's it. We are like, I looked on fact on the schedule, and it's amazing how little we have to do considering the time. Very, very likely that Thursday, that's the 30th, or not the Thursday. No, the 30th is your final. The day before, what is anyway, the day that's listed on your syllabus, I think it might be the 26th or something. The day that's listed on the syllabus as a review day, chances are we won't even be here. We won't need it. Okay, because by the 23rd, and we will be here the 23rd, by the 23rd, I would say we're going to be completely done with everything and can review that day. Okay, so we have plenty of time, unless I get on another sermon kick or something, but I'll try not to do that. Okay? All right, so let's get going on these terms. So just grab a pen and let's go. All right, evaporation or vaporization. I'm just going to give you the terminology, and then you're going to tell me some examples, okay? So evaporation or vaporization, that's changing from a liquid to a gas. Changing from liquid to gas. Changing from liquid to gas. Changing from liquid to gas.
Burning gasoline.
Not burning gasoline, but the gasoline, if you spill gasoline on the ground, what happens to it? What's it do? Dries up, doesn't it? It's like you can't see it anymore. It dries up. I've made the mistake in my garage literally right now. In fact, McKinley, take it out when you get home. I have a power washer in the garage, and that thing, the cap is just, I don't know. That thing, my garage stinks. My car stinks. I mean, it's crazy because what's that gasoline doing in that tank? It's evaporating. And all the fumes from the gasoline that's evaporating are coming into my garage. And so gasoline is in fact, I'm going to skip to this word. Gasoline is very volatile. What does volatile mean?
Explosive?
Not quite, but it goes with that, but it's explosive because it does this. Volatile is evaporates readily, quickly. Volatile is evaporates readily. Evaporates readily. Because it evaporates readily, that sometimes can lead it to becoming more volatile and more explosive rather. More explosive. We use the terms volatile for people who get angry really quickly. That's what we would use it. So that's kind of like, that's why we think of it explosion, but it's really evaporates readily. So some examples of this would be alcohol, gasoline, and yes, we talked about the fact that gasoline changes quickly so it's volatile. Any liquid can evaporate. Any liquid can evaporate. Something here I will put on evaporation or vaporization is alcohol rubbed on the skin uses heat from skin to evaporate and cools the skin. Now that's a lot to write, and you don't have to write it if you know this, which many of you do. Remember they give you a shot? Pull your shirt up. What do? They rub the alcohol pad on your arm. What's it feel like? It's a little cool, right? Why? Because guess where it's getting its heat to cause the evaporation? From your skin. So it's taking heat off your skin, which then makes your skin feel cool. So it's literally taking energy from your arm. And that's evaporation, and that's why it feels cool. Okay? Sublimation is changing from a solid to a gas. Changing from solid to gas. That's sublimation, changing from a solid to a gas. What is something that sublimes very readily? Dry ice. Dry ice. What is dry ice? Solid CO2. That's exactly right. Solid CO2. Dry ice is solid CO2. And it sublimes very, very readily. But there's something else that sublimes that you don't think of as subliming, and that's regular ice. Regular ice sublimes. Now, let me prove it to you, okay? So you have ice cubes in your freezer, right? So let's say that you either have an automatic ice maker or you have the trays. It doesn't matter which one, but trays show this really well. Let's just, and you don't even have to use a tray. You can just use a cup. Get you a small cup, a small container. Put some water in it. Don't fill it to the very, very top, because if you do, it's going to expand and go over. But fill it close to the very top. Let it freeze. Go look at it the next 24 hours, and you're going to notice it's this really, really big chunk of ice. The ice will be up to the top or even over, depending on how full you made it, and it's going to be this really, really big piece of nice ice. Leave it alone for a month. Come back and look in your freezer, and guess what that ice is going to be? Smaller. Now, did it melt? No. It couldn't have we're talking deep freezer. Put it in the deep freeze. It's like it could not have done anything melting wise because everything stayed frozen the whole time. So what happened? It sublimed. The solid H2O changed to a gas. Now, did it sublime as quickly as dry ice? No, not at all. But it does sublime. In 1998, there was a hailstorm here in Bowling Green, a severe hailstorm. Caused major damage. I was teaching at Bowling Green High at the time, and we had to close school down. Everybody in Bowling Green. For years after that, you would see pings all over cars because of hail-damaged cars. And people, that hailstorm occurred during spring break for the city school kids. And so some of the people who were in Bowling Green saved the hail balls, put them in their freezer to show their friends how big they were. Well, guess what? When the friends got back from Florida, the hail balls were not very big because they had sublimed. And that's what happened. Now, one more thing that is, it's like nobody knows this, but it's exactly what happens. Freezer burn. Freezer burn. Think of what freezer burn is. Freezer burn is, let's just say you got a piece of meat.
So cold that you burn yourself.
Nope. You've got a piece of meat. You've got a piece of meat in the freezer. You got a piece of meat in the freezer, and it's packaged, but it gets a little hole in the packaging. And you don't notice it until you pull it out. And then you see that hole, and you're like, oh man. And then you take the whole packaging off, and you notice where that hole was, it's discolored, and it's very dry looking. What does all meat have in it? Water. That hole was an opening into the package. Nobody had dried the meat out. The water in the meat had been frozen, correct? Never had the piece of meat been taken out of the freezer until you took it out. The hole, though, allowed what to happen to the water that was frozen in the meat? Sublimed. And so what did that cause the meat to do right there? Dry out. That's what freezer burn is. Freezer burn and burns of any kind are actually dehydration. That's what a burn is. A burn is dehydration. Freezer burn is dehydration, and that's what happened. This is not the same thing as touching dry ice or putting your hands in the freezer and hurting. And we're not talking about frostbite. Freezer burn is dehydration of water from the frozen meat, fruit, vegetable, whatever it is. Yes?
I've seen it on a tub of ice cream.
That's frost. It could happen freezer burn. Have you seen it actually dry out? Okay, I've never seen that. That's interesting. I've never seen that.
The thing is, it was like open, but it was inside. When I opened the container,
Uh-huh.
I was going to my big industrial freezer. You know the one, the big
Right,
black one.
right.
And I was sitting my tub of ice cream after. I opened the lid and I see. Well, I would say I thought it was frost at first.
Uh-huh.
But I realized it looked too unusual to be frost.
And it was dry. It was dried out. That's interesting. I've not seen it do it on ice cream. That's interesting. But it could, because ice cream has water in it. So it easily could. So freezer burn. So I'm going to put on here freezer burn. It's kind of interesting. It's like nobody in the real world knows what freezer burn is, but you now know. It's sublimation. All right, condensation is changing from a gas to a liquid. Changing from gas to liquid. That's what condensation is. Give me an example of that one.
It's what happens when glass hit it gets fogged up from steam and then it can.
Did it happen to you this morning when you were taking a shower?
Well, a little bit with my mirror.
Exactly. That's exactly right. That's exactly right. So example of that is when you have the condensation fog on the mirror in the bathroom. That's condensation. Condensation fog on mirror in the bath. That's something all of us have probably experienced. Can I do the same thing by blowing on my glasses? Yeah. They would condense. The moisture from my breath would condense on the glasses. All right, surface tension. Surface tension is one of the more fun things to talk about. Surface tension is the resistance of a liquid to an increase in surface area. It's the resistance of a liquid to an increase in surface area. The resistance of a liquid to an increase in surface area. Water has a very high surface tension. Water has a very high surface tension. So, give you an example of surface tension. Water bugs.
Oh, yeah, the water structure.
Water bugs.
Those water floating, those water floating mats you sometimes see out on the lake, like.
That's partly, yes. The water floating mats are somewhat, but there's a lot of other factors involved. The
That's-
buoyancy,
yeah,
there's a lot of other things in that. But just us floating on water too is also part of buoyancy.
Like when you put a penny on the table and you drop it.
Yes, if you put a clean penny on your table, if you had a clean penny on the table and you put a drop of water, the water bubbles up and it will literally bubble up over the surface of the, I mean, you can literally see the water bubbled up like this. Then if you put a drop of soap on it, it breaks the surface tension and it just rolls off the penny. If the penny's dirty, it won't bead up like that. It won't bead up. Now, to kind of give you an idea, can you all hold both? Can you use both hands and hold that? Okay. All right, hold it tight. All right, pretend this is the surface of water. I know not all of you can see this real well, but pretend this is the surface of the water. This is surface tension. See how the surface tension is, it won't let me go through it? But when water has a very high surface tension, so what happens is when a bug tries to walk on the water, does it actually go through the water? No, it holds it up. And because of the surface tension, because surface tension is the resistance of a liquid to an increase in surface area. In other words, it's pushing against you because look what happens. If you break the surface tension, so now break it, let it go. If you break it, look what happened. Look at my finger. Pretend that my finger went through the water. Did it increase the surface area? In other words, did my finger have to be surrounded by water now? So has that increased the surface area of the water? Yes. But when it was only pushing on it, that was the resistance to an increase in surface area. And that's what surface tension is. But those water bugs are probably the best example of that. Have any of you had a class where they floated a straight pin on water? You can literally float a straight pin on water. You can float a clean penny on water if you're good enough getting it in there. And it will float because of the surface tension. Because you know yourself, a penny is not buoyant. It's going to just sink to the bottom. But if it's clean and you lay it just right, it will float on water because of the surface tension. Because water has a very high surface tension. A very, very high surface tension. All right, capillary action. And here, we can put on here, example water strider or water bug. All right. Spontaneous rising of a liquid in a thin tube. The spontaneous rising of a liquid in a thin tube. So when you go to get your iron checked, if you go to give blood, they're gonna, you can't tell that it's a capillary tube anymore. Used to, they used an actual capillary tube. A capillary tube looks about the size of it's about the size on the exterior of a round toothpick. Okay, you can picture a round toothpick. Inside it's hollow though, and it's made of glass. So what they would do is they used to prick your finger, and they still do this, except the little thing they use isn't round. The part you see is not round, but there's a round tube inside of what you see. But what they do is they'll prick your finger, and then they'll put this little tube on your finger, and the blood automatically does what? Goes up the tube. That's capillary action. It goes up the tube. And then they'll check your iron level by using that. What in nature uses capillary action? Say it. Plants. Plants. What are those two words called? Fancy words. Begin with an X, one of them. Xylem and phloem. Now, who's had a plant science class lately? Which one goes up? Xylem goes up and okay. So my friend one day I said something about xylem and phloem, and she said xylem up and phloem down. I'd never heard that before, but that made I can remember. Is that what they taught you too? Yeah, and that was like cool. Yeah, I can because I knew it was xylem and phloem, but I could never remember which one was up and which one was down. And I was like, okay, I got it now. Xylem up, phloem down. I love that. And so that's what the xylem. Think about some trees, guys. Think about just any decent sized tree. Can you imagine? It's like, are there little guys up there? No, there's not. That's xylem. That's how the water and the nutrients come all the way from the soil. That's amazing. That is just amazing to me. So trees. Let's talk about trees here. Talk about. I'm just going to put blood tube. Maybe you'll remember that. Not blood, but blood tube to check iron. Maybe you'll remember that little story, and maybe you'll give blood and you'll see it. All right. So it says adhesive and cohesive forces, and that's underneath capillary action. So why does capillary action work? It's because of the adhesive and cohesive forces that exist. So adhesive forces, and I'm going to kind of make a little note here. Adhesive forces are exactly what the word has in it, adhesive. Adhesive are the forces between the liquid and walls of the container. They are the forces between the liquid and walls of the container. They're the forces between the liquid and walls of the container. Cohesive are the forces within the liquid itself. So adhesive are forces between the liquid and walls of the container. Cohesive forces are the forces within the liquid itself. So let's think about something here. I'm going to give you an example. Some of you may have been able to do this. I have a little friend, not one that lives with me, but another little guy, a friend of mine, and he is just something else. He's only 7, he'll be 8 in a month, but he's the strongest little kid I've ever seen. And some of you were like this. He can take a door like this and shimmy right up it. No problem at all. Some of you were like that. Some of you could do that. Okay? Now, when he gets in this door frame and he shimmies up it, what kind of forces does he have? Adhesive forces. So that's the adhesive forces. Now me, I have cohesive forces. Because what I would do if I were trying to do this is I would just fall down. So my forces are very strong cohesive forces because I just be like that within me. But he has adhesive forces, so he can walk up the side of the container. Does that make sense? Spider-Man has adhesive forces. Okay? So, adhesive forces between the liquid and walls of the container, cohesive forces within the liquid itself. And so when you think about that capillary tube, when you think about that capillary tube, why, and those xylem, why does it go up? It's because of both adhesive and it holds itself together. So you got here and keep it on up, here and keep it on up. Does that make sense? So that's why. That's why. Now, hold on just a minute, okay? Because these all go together. Depending upon what forces are stronger makes a difference in what the meniscus looks like. The meniscus is the curve on the surface of the liquid when it's in a thin, narrow tube container. You follow me? You're a graduated cylinder in lab, right? So the meniscus is the curve at the top of the liquid. The meniscus is the curve at the top of the liquid. Adhesive and cohesive forces determine the shape of the meniscus. Tell me water has stronger adhesive or cohesive forces? Adhesive. How do you know? Because it's concave. Does water look like this in the container? Does it try to go up? It's got a concave. Cave means, I think of it, honestly, I wish they called it sinkhole. That's what it reminds me of. I hate to say that, but it's like this. This is concave. A cave is in the ground, so this is concave. So it's got stronger adhesive forces. That's why it's concave. Mercury has a meniscus like this. That means it has greater cohesive forces. Does that make sense? So make a note of that so you'll remember, hopefully. Water, greater adhesive forces, concave. Mercury, greater cohesive, and it's convex. All right, boiling point. What is the boiling point? Give me what happens at the boiling point. Don't give me a specific boiling point yet. Just tell me what happens at the boiling point. Liquid to gas. That's exactly right. The boiling point is changing from a liquid to a gas. Now, what is it for water? Say it again. 212 degrees Fahrenheit or 100 degrees Celsius or 373 Kelvin. So it's liquid to a gas. Could I also say that the boiling point would be the point where if you're on the gas side, it's when you change back to a liquid? Come to think about that one for a minute. I'll show it to you with boiling or freezing point, then you'll get it. Hopefully. All right, what's the freezing point? Liquid to solid. What is the melting point?
Solid to liquid.
Okay. Now, is the freezing point the same as the melting point? Is the freezing point the same as the melting point? Yes. Yes, the freezing point is the same as the melting point. Think about that for a minute. What is the freezing point for water?
At
32 degrees Fahrenheit or 0 degrees Celsius or 273 Kelvin. That is the point. If you are a liquid, you change to a solid. But is that also the melting point? Is that also the point that a solid would change to a liquid? In fact, at exactly 32 degrees Fahrenheit, exactly 32 degrees Fahrenheit or 0 degrees Celsius, what are you going to have in the container? If you kept it exactly, water exactly at 32 degrees,
You'll get ice.
half ice, half liquid. It's exactly right. It's exactly right. It's going to be half and half. So now let me ask you, go back to the boiling point. Is the boiling point also when the gas changes to a liquid? Is it the same point? There's a different word, but that's the same point. And we don't have to worry about the word. I just want you to understand, if you're thinking of phases, you got to think, okay, high temperature, that the highest, whatever the high temperature is for the substance you're dealing with, the high temperature would be gas. Then it's going to cool down to liquid, and then it's going to cool down to solid. If we're going the other direction, very low temperature will be solid, warm up to liquid, warm up to gas. Does it make sense? And the 2 points, boiling point and freezing point, or boiling point and melting point, that's where you've got equilibrium between the two phases. So if you're at your exact boiling point, you're going to have half vapor and half liquid. If you're at your exact freezing point, you're going to have half solid, half liquid. Yes or no? Okay. All right. Heat of fusion, heat of vaporization, I'm just scratching them out. We're not going to talk about those in here. All right, water properties is honestly stuff you already knew from the past. I'm just going to remind you of the properties, some of the properties that you've dealt with water. What information out of these things can you tell me? Some of it's a repeat of what we've already said. What are some things you can tell me out of this? Melting point, come on. Do you see MPT, BPT, density, SH, effective temp? Come on. What's MPT? I'm going to put them in this order. 0 degrees Celsius. Boiling point, 100 degrees Celsius. Specific heat. Anybody remember that? The units are either calories per degree Celsius or joules per degree Celsius. What was water? Say it louder, I can't hear you. 1.0. 1.00 calories per gram degree Celsius. Or 4.184 joules per gram degree Celsius. All right, and then it says the effect of density or effective temperature on density. What do you know about that? What do you know about the effect of temperature on density? What do you know? What does temperature do to the density of water? Does it change it? Okay, tell me what it does. Which one? Cold or hot?
It's cold, it gets more dense.
You do the opposite.
Yep.
When it's cold, when water gets colder, it becomes less dense. Nope. Hold on. It does have more oxygen dissolved in it, but that's not why it gets. As water gets colder, it becomes less dense, which allows water to what? Allows ice to what in water? Float. It allows ice to float in water. As water gets colder, it becomes less dense, which allows the ice to float in water. Now, what's interesting is, when you think about that, is this property the same as most other substances? What happens when metals get colder? What do? They contract, don't they? They get more dense. Metals get more dense, okay? But anything that has water in it gets bigger. Now, there's problems with that. Construction management people, there's some problems with this. Tell me some problems with this that this property of water can cause.
With concrete and stuff, if there's a crack, when water gets in there, if it freezes, it expands, opening that gap, and then melts away, so it's bigger.
So what about the concrete itself? What's concrete itself have in it? Water. So what do they put in large expanses of concrete? They have put gaps. They put gaps. And in brick and concrete walls and brick and concrete walks, they will typically put gaps. If you look at any buildings that are strictly concrete or stone buildings and floors and sidewalks, you see automatic cracks in them, like sidewalks especially. You know how you have that automatic crack? And like in our garage, for instance, when the guys were laying concrete or pouring the concrete in our garage, they went back and they cut. And those are the expansion joints. And they do that because they know that concrete, it's almost like it's alive in a sense. It's not alive, but because of the water in it, it expands and contracts. And so they go ahead and put the cracks in it, because otherwise it'll find its own natural crack. And so if you want the crack, you put the crack where you want the crack instead of them doing it, instead of the concrete producing a crack. The same thing in buildings, walls, concrete walls oftentimes, and you've seen this possibly too on the sidewalks, you'll see, and like I know at the elementary school where I subbed, there is on the whole brick wall, you just follow along the brick wall, and you'll see a gap that looks like it's filled with caulk. And it's really not caulk, it's usually just more of a rubber something. And basically what happens is that brick, in the wintertime, that gap will be smaller. In the summertime, that gap gets bigger. Because in the wintertime, the water in the brick causes the brick to shift. But if they don't put that expansion joint, then what happens is you get cracked brick, and you'd rather put the crack where you want the crack. Okay, so does that make sense for those? I mean, that's a construction management completely thing for you guys. Water and the properties of water are something that you are going to deal with. And all of us have to deal with it. Why do your pipes freeze and burst? Because of the expansion of the water. Now
yeah, that's what happened with. I think that's what happened in that stuff was small.
Did that happen? Yeah. And when they get colder, and when they get if you live in an older house that has outside walls, or any house that your walls, your plumbing walls, you have plumbing sinks and tubs, etc. on the outside wall, oftentimes if it gets below freezing for a very long period of time, especially it's going to be below zero here for a really long period of time, it's a good practice to leave your faucet on a drip and leave your cabinet doors open, so that the temperature of the room will get into that water and keep it thawed out. Because otherwise you'll have the water in the pipe will freeze and it expands, and then you don't know you have a break until it warms up. Because when it warms up, it contracts again, and then the water melts and you found your crack. And that's what happens. Okay? And so water lines, all of us are going to have to deal with this. Water, that property of water is great, because in ponds, where do we get the ice first? On top. And in the past, whenever we didn't have bridges and we lived in a very, very cold area of the United States, what did they do with that ice? That's the way. If you've ever read Little House on the Prairie, how did little Laura and Mary and the whole family get across the lakes? They drove on the ice on the Great Lakes because they were frozen. And if we didn't have that property of water, you couldn't do that. What allows you to go ice skate? It's what keeps fish alive all winter long. It's because it's ice on top and it's still water on the bottom. It has to be really, 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 really cold to get all the way down that entire pond or the lake completely frozen. So it's a wonderful property, but it's also a very hard property to deal with sometimes. You have to understand it, and we have learned that in construction management. That's you guys have got to understand the properties of water. All right, hydrates. Hydrates you dealt with in lab. All I'm going to do here is talk a little bit about what a hydrate is and how to name it, and this is more of a refreshment compared to what you've had. Okay, it's not new information because you've done this. A hydrate is an ionic compound with water loosely attached to its structure. It's an ionic compound with water loosely attached to its structure. So I'm going to give you one name, and you're going to write the formula for me. So the name that I'm giving you is barium bromide dihydrate. Barium bromide dihydrate. Barium bromide dihydrate. So what do you do first? Make the ionic compound. Good, Josh. Do balance the charges. You got to balance the charges, and you're basically going to write the formula for the ionic compound first. So what's barium's charge? +2. What's bromide's charge? -1. So what's the formula of barium bromide? Okay, so BaBr2, and then we put a dot to show that it's attached. So we put a dot, and then how many waters do we have? 2 H2O. So that is barium bromide dihydrate. Remember this from lab? All right, I'm going to give you another one for you to name. So FeSO4 dot 7H2O. FeSO4 dot 7H2O. Ionic compound, so you got to pay attention to your who it is. Pay attention. Who is this? It's iron, but what's special about iron? It could have multiple charges. Good job. It could have multiple charges. So what do you have to figure out first? Who is sulfate? What is sulfate's charge? Okay. So which iron is this? So the name is iron 2 sulfate. Keep going. Iron 2 sulfate, hepta, what? Hydrate. Good job. Iron 2 sulfate heptahydrate, or could iron 2 be called ferrous? Ferrous sulfate heptahydrate. I know this computer just acts like it's going to take off some days. Okay? I think somehow it's doing that. Okay. All right. Anhydrous. What is an anhydrous? And it's not properly used in farming. The term anhydrous is not, the term anhydrous in farming is treated as a noun. It's treated as treated as a substance. I'm going to go spread some, what are you doing today? I'm spreading anhydrous. No, you're not really spreading anhydrous. You're spreading anhydrous ammonia. Ammonia is what you're spreading. It is an anhydrous. What is an anhydrous? Think of the word. It doesn't have water. Anhydrous means no water. Anhydrous means without water. Without water. So an anhydrous has no water. Most of the time when you say anhydrous something else, like anhydrous ammonia, it's in regards to a substance that does like water. You just happen to be using a substance that at that moment doesn't have water. So anhydrous ammonia is NH3. That's what anhydrous ammonia is. Anhydrous ammonia, it's terrible writing. Anhydrous ammonia is NH3. In labs that you've done this semester in chemistry, you have had a lab, maybe two, that said use ammonia. And there would be no ammonia on your bench. And then we would tell you use ammonium hydroxide. Because anhydrous ammonia doesn't stay anhydrous very well. Because it immediately wants to seek out water. Just boom, it's going to find that water. And so anhydrous ammonia plus water makes ammonium hydroxide. And that is what we use. This is much safer. Ammonium hydroxide is much safer than anhydrous ammonia. This is very unsafe. Why is it unsafe? It seeks water. It absolutely seeks water. When or if you ever are around anhydrous ammonia tanks or equipment that is spreading anhydrous ammonia, you need to be extremely careful. Why? It takes all the water out of your eyes and your nose and your skin and your mouth, and it will absolutely burn your membranes because it's seeking the water, and that's where the water is. I heard a funny story the other day about a man who's a farmer who went to, with his wife, she was giving birth to a child, and he passed out in the delivery room, and he was a farmer. Well, they kept putting ammonia tablets. They took this anhydrous ammonia. They break a little vial of it to try to get you to wake up because it's so vile and volatile. It evaporates easily, and you smell it, and it'll wake you up. Well, they did it a couple of times, and he was not coming to. And his wife, who is giving labor at the moment, says, "Dude, he's been spreading anhydrous ammonia. He can't smell that. You just might as well let him wake up when he gets ready to." Because his membranes were fried, and he'd been around this ammonia so much, that little vial wasn't going to faze him. He was out for a bit. And so it's dangerous. It's very, very dangerous. And I'm the world's worst about proper protocol as far as using gloves and all that. We've tried to start being better on the farm of using gloves when we're deworming and using gloves when we're using chemicals. Because it's hard. It's a habit you have to get into. But I will say, when you're dealing with anhydrous ammonia, please, for your sake, use the safety precautions that they tell you to use. But use those, because it is extremely dangerous. And it's because it is so hygroscopic. What does hygroscopic mean? Water loving, water seeking. So hygroscopic things are very much water loving, water seeking. Anhydrous is without water, and it's anhydrous at that moment, but it usually is something that's hygroscopic, and it's going to go find the water. Okay? What are some other things in the real world that are somewhat hygroscopic in the kitchen? Sugar. Have you ever gone into your cabinet to get sugar out and it was like clumped up into clumps? What do they put in I just told you the answer. What do you put in salt shakers to keep them from getting clumped up? Rice. And the reason for that is because salt is hygroscopic. And that's why. I guess if you had a sugar shaker, you could put your rice in a sugar shaker, but I don't. Okay. All right. So let's stop. That's a good place to stop. Y'all be thinking about a sugar shaker now. Lucas is going to be like, what's a sugar shaker, Miss Brooks? There is no sugar shaker, Lucas. See you when you get home.